So I thought it might be helpful if I played around with the trust analyzer a bit and pointed out some things that I've noticed. So that's what I'm going to do in this video. The first thing I'm going to do is, I'll point out that I've set this up already. We have our equation, our F max equals minus 35 times length plus 320. And as we discussed in class, this comes from our empirical data that you guys all generated through experimentation earlier in the class, and this is where we plotted force against specimen length, and Nico has then taken all that data, created a trend line, which is what this formula is, and that we put in the trust analyzer, and so therefore we have a theoretical, or no, actually an experimentally derived strength for our members. Or for our material. Okay, so let's just go ahead and make a very simple truss. I'm going to add a joint at 4 inches. Remember that we have a 15-inch long truss that can be up to 4 inches tall, so I'm just going to use those as my limits, those measurements. I'm going to add a couple of members here and make the simplest truss we can make, a triangle. And I'm going to apply a 100-pound load. Choosing 100 pounds because that just is a simple thing to a simple number, and then for other calculations it'll make things a little bit simpler as we move forward if we're trying to compare trusses, for example. First thing we notice is that I applied this force. Our max load is pretty low, 21 pounds, and there was some confusion in class that I was responsible for, so let me, in addition to posting that announcement that I did, let me point out again that this max load in the truss analyzer is the failure load for the truss. It has nothing to do with a specific member. It is the failure load for the truss. So we see that we would fail at 21 pounds of pressure applied, or 21 pounds of force applied to the truss. Another thing to notice here is that that's interesting is that we have these two members that are failing in this case are actually taking more force than is being applied, and that may seem like an error, but in fact, if you go and do the method of joints for this truss, and I won't go through it. I think you guys have started doing this in class, but there's a process by which you can manually do what the truss analyzer does, and we see that going through this process, we do actually get a negative 106.4 for the AB. So this on this member AB. And we get a 93.95 in my case on this member AC, which is almost identical to what we get in the truss analyzer, 106.3 and 93.75. I'm not sure why it's 7.5 instead of 9.5, but I think we can just say it's close enough. So that's, anything that we're doing with the truss analyzer, you could do with the method of joints and the method of sections. And I think you should learn to do that, and you probably will in the other class, but that's not something we're doing in this class. All right, so let's play around with this truss then, and I think this is the thought process that I would be using if I were you trying to design a truss that's using this as a tool, the truss analyzer, that's going to be as strong as it can be using the least amount of material. So let's mess around. I'm going to delete this member. I'm just going to, I probably don't need to do that. I'm going to add a joint here, and I'm going to add some members. And we see that did nothing at all. But we do it, so this member in the middle now is actually taking no force. The force is still being taken completely by these two members, or the compressive force. Something to point out is that if it's negative, it's in compression. If it's positive, it's in tension. And that's, again, if you go and look in your textbooks and study free body diagrams and these methods of calculation, you'll see why that's true. Okay, but the reason I added this joint is that I'm thinking, okay, if these two members are going to fail, and they're failing because of their length, right? The shorter, if the force is the same, the shorter or the more members that we can get to take that force, the stronger the truss will be. So let's try something else here. I'm going to turn off my labels so that I can see this more clearly. One thing that bugs me about this Truss Analyzer program is it's hard to place joints. Oops, joint. But they seem to work. I want to place a joint equidistant between these 2 points here. Now I'm going to delete this line. This is a mistake that I have made myself. I'm going to delete this member because I need to add a new member between these 2 points, or between these 2 joints. Even though it looks exactly the same, it's not the same. So I'm going to add these members back. And we see the result is that our max load is now at 161. So by simply breaking up this one member into 2 pieces, basically we now have 4 members taking that same load. So we've drastically increased, I wouldn't say drastically, but we've increased from 25 or 21 pounds required to make the truss fail. We've increased it to 161 just with this simple move. So this is the kind of stuff that I would, if I were you, I would be doing to mess around with the Truss Analyzer and see if I can find. So what I would do now is I would try to apply this principle to other trusses I was designing and see if I can create a larger construction that has the same, or that takes the benefit of this approach. So let's look at another thing now. We talked about keeping track of your data as you're designing these trusses, and this is a simple way of doing that. You know, you could add more to what I'm doing here, but I just wanted to. We talked about this in class, but I didn't go over it, I think, in a way that was clear to everybody. I'm going to actually, let me see what our member names are here. They may be different. No, it turns out the same. So I guess I made this in the same way as the one that I used to create this spreadsheet. So this is a simple spreadsheet that is, I'm pulling information from the Truss Analyzer into this spreadsheet to keep track of this data and to make an analysis. So in this case, let's just look at it. So we have our equation up here, y, which is the force equals minus 35x plus 320. We have a column for all of the members that are in compression. And so if I look back at my Truss Analyzer, M6 and 7, M2 and M4, so those are here in this row. Then the second row is member load over applied load. And where I get that is from, if I look back at the forces, if I divide the member load, so in this case, for all of these members, it's 106.3, by the applied load 100, I get this load factor. In this case, it's more than 1.063, and it's the same for all 4 members. I can also get my links from the Truss Analyzer, and again, with this simple truss, all of our members that are in compression are 4.25 inches long. So that's in this column. And then I simply take our equation that we derived from our experiments and input our length into it to get I guess you could call it the pure compression critical buckling load for each of these members. Again, since they're all the same length and are taking the same load, the number is the same, 171.3. Then, if I want to figure out at what point this truss is going to fail, I take this member load and divide it by the load ratio from B2, column B2, and I look for the smallest number of all my compressive members, and then whichever one is basically whichever of my members fails first is going to tell me what my the failure load for the truss is. So that's what we have here. Let's look at a slightly more complicated example. I'm going to open another file. So this is the spreadsheet for this simple trust. You can see this is actually quite a bit stronger, and we've only added one triangle here. This is a 5-triangle trust. Well, that's just what I'm calling it. The other had 4 triangles. And the same thing, if we, let me apply a 100-pound load. Delete this load. If we apply 100 pounds of load, then we can, first of all, we see which members are in compression. The ones with a minus, in this case, they're red in the truss analyzer. Green is tension, red is compression, and yellow is failure. Blue is no load. So in any case, we can see then that's where I'm getting these numbers here. You can either divide it out or just put a 100-pound load to it, and that's your percentage. So these members here have a 0.625 load factor, whereas these in the middle have a 0.59 load factor. Then, again, here are my labels. I pull the links out of the truss analyzer and make my calculation for the critical buckling load, and from that I get the load at which the truss would fail based on that member. And we see down here that we're getting the same result as the truss analyzer, that the members that have the 62.5 or the 0.625 applied load or load ratio will fail at 145. When that's multiplied or divided by the load ratio, that means that the truss fails at 232. And we see over here in our truss analyzer that is the number we get for our max load or our failure load. So that's the way we can tie a spreadsheet to the truss analyzer, and this then the spreadsheet becomes basically a running tally of our different, or sort of it's a place where we're storing the data that we're generating with the truss analyzer in a way that we can compare different trusses. We could also add to this the rest of the members, the ones that are in tension, to get and we would use those in addition to the ones in compression to keep track of, for example, weight, and then we could do a strength to weight ratio calculation, which in the real world would be very important. It's not part of our assignments for the competition, but it might be a good thing to have in your reports. I'll let you decide that. Anyway, fairly boring video, but I think that it covered more clearly, or you can stop and pause and go through it with you could emulate what I did here yourself with a truss analyzer. And so if there were any lingering questions in class, hopefully this will help clear them up. All right, I will see you guys on Tuesday.